Alright, so all faults which displace material vertically will have a footwall block and a hanging wall block. And knowing the motion of either block relative to the other one will determine if the fault is a normal fault or a thrust fault, basically. So let's go ahead and draw that as you go. So, excuse my drawing, it's not very good with this. So this is my block. I'm going to split it by some fault. And then I'm going to have some layer that was initially here, but now is down here. So, in order to determine whether my block is a footwall or a hanging wall, a typical and useful thing to do is to draw a little person that is being cut by the fault. So the little person is always vertical, so it always appears perpendicular to the horizontal. And wherever the feet of the person fall is going to be the footwall, unsurprisingly. And wherever the head of the person falls is going to be the hanging wall. So, in a normal fault, the footwall is going to always move up relative to the hanging wall. Or if you want to say it another way, the hanging wall is always going to move down relative to the footwall. So, another example of a normal fault looked a little bit different. Could be the following. So if I have, this is my fault, this is my layer here, and this is the rest of my layer here. In this case, if I draw the little person, the feet of the person are here. So this is a footwall, this is a hanging wall. So you're seeing that the hanging wall moved down relative to the footwall, or the footwall moved up relative to the hanging wall. So again, in a normal fault, the hanging wall moves down relative to the footwall, or footwall moves up relative to hanging wall. Okay? For a thrust fault, the opposite is going to happen. So let me erase that. So if I have a block, let's put the fault in the opposite direction than the example on the left. So that is my thrust fault. I have a layer that initially used to be continuous, but now appears discontinuous. One side, the left side, which we now know is the hanging wall, because that's where the head of the person came. And again, we see that, I'd erased it. Ugh. Sorry, guys. Let me draw that thrust fault again. So, we have our block, we have our fault, we have our layer that used to be continuous, but now it's not. We have our person. This is the footwall. This is the hanging wall. So in this case, the hanging wall moves up relative to the footwall, or the footwall moves down relative to the hanging wall. Okay? So in the opposite case, where you have the fault the other side, like there is in this example right here, you're seeing that this layer, which is a hanging wall, or this fault, sorry, or this block, which is a hanging wall, is moving up relative to the footwall. So you're seeing this layer is above the same layer on the footwall. Okay, so I hope that was a little bit helpful. It helped me when I first started doing this little drawings with the man. that has been cut by half. Wherever the head falls, hanging wall. Where the feet falls, foot wall. If the hanging wall moves down relative to the foot wall, that's a normal fault. If the hanging wall moves up relative to the foot wall, that's a thrust fault. Okay, so at a transform plate boundaries, so where two plates move past one another without one being subductor under the other, or without any new mass rising to the surface and occupying the space that used to be occupied by the plates when they were together. So again, this type of boundary, where the two plates are simply sliding past each other, transform plate boundary, is associated with strike-slip faults. So a great example that we have of a strike-slip fault is the one that we discussed a little bit earlier in detail, the San Andreas fault. So as we saw in Chapter 2, you may remember that where there are transform boundaries, they typically present in some sort of subsections. So they split the mid-ocean ridge system, for example. But they will also subdivide into smaller kind of branches, as is the case in the San Andreas fault, like you're seeing over here. So as you're seeing in the figures at the bottom, both of them, you can see that there is branching of the fault. They're being subsectioned into a northern part, northern San Andreas fault zone, a central part, the central San Andreas fault zone, and then a southern part, the southern San Andreas fault zone. So strike-slip faults can be either right lateral strike-slip faults, like the San Andreas fault, or they can be left lateral, which we don't have an example to show you right now within the slide, but we're going to go ahead and draw that in the next slide. So the way in which you define whether a strike-slip fault is right lateral or left lateral is by locating a feature that got displaced from its original location by the movement of the two blocks sliding past each other. So if, for example, we have a block as that one, and it has been split by a fault, this is looking at it from above on a map view kind of perspective. This specific block used to have a road that used to be together before the fault, but now has moved and has displaced as such due to the fault's movement. So we know that the right side moved a little bit further, I guess, south, and then the left side moved a little bit further north. So again, we're going to locate that feature on one side of the block. So we're going to locate this feature, basically face the other block. So if we were standing here and we were facing this side, and then we would look at that feature on the other block, that feature would appear to us on our right side. If we stand on this block and we look at the feature on the other blocks on this block, that feature appears to us on our right side. So let's draw another example. So if we have, again, some block, this is on a map view perspective, again, looking at it from above, and you have some fault, and you have, let's say, a stream this time. So in this case, you see that the stream on the right side of the block looks as if though it has moved to the north, and then the stream on the left side block looks as if though it has moved to the south. So if we stand on the stream and look across the fault to the other block, we see that the stream, so that feature appears to us as if though it was left, on our left. So it's a left lateral strike slip. If we stand on this side of the fault, on this block, and we look across the fault onto the other block, the feature, so the stream, appears to us as if though it was to our left. So definitely a left lateral strike slip fault. All right, so after having covered those different types of faults associated with the different plate boundaries, now we're going to move on to seismology. So seismology is the study of earthquake waves, and it dates back to attempts made in China almost 2,000 years ago. So Chinese tried to determine the direction from which these waves originated. The first instrument that they used was a large and hollow jar, like you're seeing over here. Over here, with a weight that was suspended from the top, as you're seeing in the image. The suspended weight was connected to the jaws of several dragons. So there were about 8 dragon figurines that were attached to the jar on the outsides. Each dragon itself held a metal ball, and when the earthquake waves reached the jar, the weight inside of the jar would move in one direction, causing the dragons, or the specific dragon that it triggered, to open its mouth and release the ball into the frog's mouth that lied directly below the dragon's mouth. So, in principle, this method that they used, this instrument, told the direction of where the earthquake waves came from. And also in principle, modern seismographs or seismometers, which are instruments for measuring seismic waves, are similar to this ancient Chinese instrument. So a seismograph has a weight that is freely suspended from a support, like you're seeing in the image over here. So this is the suspended weight, this is the support. And the support is securely attached to the bedrock underneath it. So when the seismic waves reach the instrument, the inertia of the weight keeps it relatively stationary, while the earth and the support will move. So you can think of inertia itself as when objects are at rest, they tend to stay at rest, and when objects are in motion, then they tend to remain in motion. That's basically the law. And they tend to do this unless they're acted upon by an outside force. So an example of inertia is, for example, when you're driving and you have to stop very suddenly. When you do so, the car slows down, but your body will move a little bit forward in the seat because it had been moving that way initially. So it wants to continue to be moving that way. So most seismographs are designed to amplify the ground motion in order to detect very weak earthquakes or very large ones from far, far away. These instruments are made to withstand very great amounts of shaking, which can occur at the epicenter of an earthquake, for example, or simply at areas very near the epicenter. So once the seismograph has recorded the data, these records, which are called the seismograms, so this would be the seismogram, this rolls basically, containing the records, are typically sent back to the observatory, and they're analyzed for pinpointing out the location of the earthquake. And we'll do that in lab, for example, and I'll teach you how to do that in the next few slides as well.